So till now, we have discussed about criteria for precipitation, then how microstructure and interface between the matrix and precipitate they change during aging treatment, and then how dislocations interact with precipitates and how the interaction changes during aging. Right? We have discussed all these, and also we have discussed about how the strength and hardness changes with aging with respect to radius and aging time. We have discussed that, right? So today what we are going to discuss is the effect of temperature first. So what is the effect of temperature on the aging curve? And then we will talk about the dispersion strengthening. Okay. So let's talk about first effect of temperature. So to understand that, let me first draw the phase diagram. Okay. So we have temperature here, then weight percent of say B, right? So we are talking about A and B, and we have discussed about the alloy, aluminum 4% copper alloy. Okay. So here we are talking about A and B. So this is alpha, which is single phase. Then we have alpha plus L, and then alpha plus beta. Okay. So now let's take two temperatures here. Say we are aging the alloy. We are taking say this particular composition, okay, having the concentration of C0, and so this will be something like this, right? This particular composition. Now let's take two alloys here. One is at temperature T1 and another one at temperature T2. Okay, and here T2 is greater than T1. Okay. Now, since we are aging it, beta will come out from the alpha matrix, and this beta is actually precipitate. Okay. So if we age it at T1, we are going to have this much of beta volume fraction eventually at equilibrium condition, and at temperature T2, this is the beta fraction, right? If you use lever rule, you are going to get the volume fraction of beta and alpha respectively, right? So the here this much at T1 and this much at T2 is your fraction of beta in the microstructure. Okay, so let's talk about it. So at high temperature, so in this case T2, what you are going to see is smaller volume fraction of precipitates. Okay, so you can see here at T2 you have very small volume fraction, right, compared to at temperature T1. So T1 here you have higher volume fraction. So at lower temperature, T1 you have higher volume fraction. Of precipitates. Okay, so now you already know, depending upon the volume fraction, your hardness is going to change, isn't it? So the higher the volume fraction of the precipitate, you're going to observe the higher hardness of the alloy, right? So this also means that at lower temperature, which is T1 here, you are going to have higher hardness of the alloy compared to a temperature T2, which is higher than T1. Okay, so as you increase the temperature, since the volume fraction of the precipitate decreases, the hardness of the alloy is also going to decrease. That is point number 1. Okay, now the second is, at higher temperature you have more driving force, right? Diffusion is faster. That means you have higher kinetics. What does it mean? It means that the precipitates can form much earlier, right? If you are at higher temperature, because the diffusion is more there, isn't it? And at lower temperature, you have lower kinetics. So as you increase the temperature, in this case from T1 to T2, the kinetics also increases. That also means that the precipitate formation is going to be faster when the temperature, agent temperature, is increased. Okay, this also means that the time to reach the peak hardness is going to be lower at higher temperature. Okay, so that suppose we have a peak aged hardness for lower temperature is H1. Okay, and at high temperature H2, the peak hardness I'm talking about, then the time to reach H1 will be higher than the time to reach H2. Okay, so these are the two things we need to know. So the first point is, as temperature increases, what is going to happen? Your hardness is going to decrease. That is point number 1, because the volume fraction of the precipitate is going to decrease. Now second point, as temperature increases, time to reach peak hardness is also going to decrease. Okay, so when you increase the agent temperature, both hardness as well as time to reach peak hardness will also decrease. Okay, so these are the two things you are going to observe with respect to agent temperature. So now if I plot the aging curve, we have discussed aging curve, right? So let's now plot, and whatever we discussed before was for a particular temperature. Now we are changing the temperature. So let's look at it, how it is going to change with aging temperature. So we have hardness, then aging time here. Okay, so you're going to have some hardness even if you don't age it, because of solid solution is strengthening, and that will be our next topic. Okay, so you're going to see something like this. Okay, say temperature T1. Now if I increase the temperature, you're going to see something like this. Then if I increase furthermore, it is going to be something like this. Okay, so T1, T2 and T3, where T3 is higher than T2 and then T1. Okay, so so this is your peak hardness at temperature T1, and time to reach the peak hardness, which is small t1, okay, at temperature T1. And then this is your peak hardness at temperature T2, and the corresponding time, let us denote it using T2. And then at temperature T3, the time to reach the peak hardness. So let me also write. So okay, so this is your T3 here, and let me write the pith hardness value H1, H2, H3. Okay. So the sequence will be S3 is going to be lower than H2 and then H1, and similarly T3 is going to be lower than T2 than T1. Okay, so as you increase the agent temperature, which is here, okay, your both hardness and time to reach the peak hardness is going to decrease, and that is what is observed in the aging curve I have drawn here. Okay, so now you know how the precipitate size etc. changes with respect to time, and how the aging curve changes with respect to time at a particular temperature. Then we just learned how the aging curve changes when you change the aging temperature. Okay. So now let me go to another important point. So if you remember, when we are talking about the steps for agent treatment, steps for precipitation, right? The first step was solution treatment, then we quenched it, and then we aged the alloy, right? So then our question comes, why do you want to quench it, right? Why don't you slow cool it and form beta, right? Anyway, the equilibrium structure based on the phase diagram. So if you see here, based on the phase diagram, the equilibrium structure is alpha plus beta, isn't it? So if you go to alpha region, single phase region, and do solution treatment, you could have slowly cooled it and formed alpha plus beta. Why do you want to quench it first and then age it again, right? And wasting some amount of energy by heating it again, isn't it? Right? So what is the necessity of quenching it rather than slowly cooling it after you have solution treated the alloy? Okay, so let's understand that concept. So the question is, why do we need to quench the alloy after solution treatment we are talking about? And not slowly cool it? Okay, because based on the phase diagram, we are going to get alpha plus beta even if we slowly cool it. Okay, so let's understand that. So suppose you are going to high temperature. So you are in this particular region. Okay, I have phase diagram here now. So you are here. Okay, then we are quenching it rather than slowly cooling it. So what is happening, right? If you slowly cool it, the process is very slow, and consider it that you are doing everything at high temperature and then you are slowly cooling it to room temperature. So you are spending sufficient amount of time at high temperature so that you the diffusion is faster there. Okay, because you are spending sufficient amount of time at high temperature. Okay, while you're slowly cooling it. So what will happen if you see your microstructure after slowly cooling it? You have said these drain boundaries. Okay, so since you are slowly cooling it, you are giving sufficient amount of time for B atoms to come out from the alpha matrix, if this is alpha here. And we have alpha plus beta. So B atoms will come out from the alpha matrix and they are going to form beta phase, right? And since we are giving sufficient amount of time and the temperature is also higher, you have lots of diffusion going on. There is a possibility that the atoms here, they will diffuse to grain boundaries and they are going to form precipitates at the grain boundary itself, something like this. Okay, because the diffusion is faster, you are given sufficient amount of time also. So atoms have sufficient driving force to move from interior of the grain to at the grain boundary and form beta phase. Now these beta phase are what? They are intermetallic in nature, right? So they are brittle in nature. Now if you start doing tensile test of this particular alloy, this beta phase is going to fail right away. Okay, so you are going to get intergranular fracture. So this beta phase here, they are going to fail all this, right? And you are going to observe fracture through the grain boundary. So we call it intergranular fracture. Okay, and you don't want that, isn't it? The whole purpose of doing aging treatment is to increase the strength, but you don't want to lose ductility completely. Okay, there should be sufficient ductility as well if you want to, if you are increasing the strength. Okay, so what do we do? Instead of slowly cooling it, so this is the case of slowly cooling. So instead of slowly cooling it, we are going to quench it. So if you quench it, you're going to form supersaturated solid solution. We have discussed that. Okay, and now you are heating it again, but remember, you are not heating it to a very high temperature, right? And but your B atoms, they want to come out because that is not equilibrium condition. The supersaturated solid solution is not at equilibrium still, right? So B atoms will want to come out. So if you remember, we had discussed this before. So if I am aging it at this particular temperature, so there is this much of supersaturation, right? Equilibrium suggests, this phase diagram suggests that the solubility is only here, right? But we have extra B atoms, this much. So these much B atoms will try to come out as soon as possible so that the whole system is in equilibrium. Okay, but you are not at very high temperature when you age it, right? But you are giving some driving force so that atoms don't move. But again, atoms want to come out quickly and then form beta phase because they want to achieve go through achieve equilibrium, right? So what will happen? They will start forming precipitate inside itself. Obviously, you are going to observe some precipitates also at the grain boundaries. No one is denying that. But apart from the grain boundaries, you are also going to observe precipitates interior, inside the grain. Okay, now if you compare the one microstructure where we have slowly cooled it, there you had a continuous film of Al2Cu, if we are talking about aluminum copper or say beta phase. Now if you compare, you don't have a continuous film of beta phase. They are distributed inside the grain as well as grain boundary, and this is what we want. So you have sufficient ductility also. So this is the structure of quenching plus aging. Okay, so you are doing both here. So that is the reason why we first quench the alloy and then age it. We do not slowly cool it. Okay, so that we can avoid the formation of beta phase at the grain boundary, continuous film of beta phase at the grain boundary. Got it? Okay, so this is much I wanted to discuss in precipitation strengthening. So what I'm going to do now is to talk about something called dispersion strengthening. Okay, so we'll discuss about dispersion strengthening. Okay, the name suggests, you have dispersed something, and because of that, you are getting some strengthening in the alloy. Okay, so now the question is, what do we disperse? Okay, so let's understand that. So in this mechanism, the strength is enhanced by the addition of dispersed voids. Okay, so you are adding dispersed voids, and these dispersed voids are actually hindering or say restricting the movement of dislocations. Remember, when I started talking about strengthening mechanism, the first thing I mentioned that the whole mechanism, all these mechanisms are based on the restriction of movement of dislocations. Okay, so previously we talked about precipitation strengthening, where precipitates were responsible for the restriction in the movement of dislocations. Here, dispersoids are restricting the movement of dislocations and thereby increasing the strength of a given alloy. Okay, so what are dispersoids? So they are hard and insoluble second phase okay. So I will tell you what do I mean by insoluble second phase. Okay, so now let's consider the difference between precipitates and dispersoids, right? So if you remember, the precipitates, they are forming from the matrix itself. So when you quench it and then age it, this beta phase were coming from the alpha matrix, right? So these precipitates were forming in situ. They were coming out from the matrix itself. In dispersion strengthening, these dispersoids are added from outside. So you are adding, say, oxides, nitrites, so some hard particle. Okay, you are adding it from outside. So that is one of the differences between precipitates and dispersoids. Now, second difference is that if you talk about precipitation strengthening strengthened alloys, if you go to high temperature, right, those precipitates which you have formed during aging treatment can again dissolve back, right? And that was the first treatment, if you remember, the solution treatment itself, right? So the precipitation hardenable alloys, those are, they are not very suitable if you want to work at very high temperature, because the precipitates will dissolve back and then the strengthening will be lost. Okay, if we compare that to dispersion strengthened alloy, the dispersoids on the other hand, they are insoluble at higher temperature. Not, we are not talking about to melting point. Okay, we are talking about a temperature like in precipitation hardenable alloys, we are talking about, say, solution treatment temperature. So in the same range, if you talk about for dispersion strengthening alloy, these dispersoids, they are not going to dissolve. Okay, they will be stable there. Okay, that this also means that these type of alloys where we are adding dispersoids, they are suitable for applications at higher temperature as compared to precipitation hardenable alloys. Okay, so these are the two main differences you have between dispersoids and precipitates, and correspondingly dispersion strengthened alloy and precipitation strengthened alloy. Okay, so let's write it down very quickly. So dispersoids you add it from outside. Okay, and if you remember, precipitates, they formed from the matrix. Okay, like beta phase formed from the alpha matrix. Okay, but here we are adding from outside dispersoids. Okay, now the second difference is dispersion hardened systems maintain strength at high temperatures. Okay, and if I talk about precipitates, so in the bracket when am I writing, there is a contrast, right, between dispersion hardened system and precipitation hardenable alloys. So in precipitation hardenable systems, precipitates will dissolve back. In the matrix. Okay, and this also means not very suitable for high temperature. Say solution treatment temperature, something like that. Okay, why? Because you are dissolving the precipitates back into the matrix. So if precipitates have dissolved, there is no one to restrict the movement of dislocations, right? Obviously there will be some lattice resistance there, but you are going to lose the strength you had achieved while aging. Okay, so these are the two main differences between precipitation hardenable system and dispersion hardenable system. So 1 and 2. Okay, now what are the examples? So if I talk about examples for dispersion hardenable system, you have aluminum and then say Al2O3, okay, or say copper Al2O3, and then one of the famous is ODS steels, which are being used in nuclear power plants. So ODS means oxide dispersion strengthening steels. Okay, so these are ferritic steels with high chromium. Okay, and then you are adding yttria, so Y2O3. So you are adding yttria, they act as a dispersoids in the matrix, and thereby they provide strength at higher temperature. So these are being used, these ODS steels are being used in nuclear power plant also. Okay, so now we know that the strength is coming from the dispersoids because they are restricting the movement of dislocations. Now what is the mechanism? So if you remember previously when we were talking about precipitation hardenable alloys, we discussed about two mechanisms. So dislocations can either bypass the precipitates or dislocations can touch the precipitates, right? Now that will depend upon whether it is coherent, incoherent, or also the size, right? And we discussed also that if the size is small and the precipitate is coherent, right, then it is going to shear. Now this dispersoid, since you are adding from outside, in most of the cases, the interface between the precipitate, or dispersoids and the matrix is going to be incoherent in nature. Okay, this also means that in most of the cases, dislocations are going to bypass the dispersoids. They are not going to cut it because the interface is incoherent in nature. Okay, So that is the mechanism. So mechanism, if you see, the interface between the matrix and dispersoids is incoherent. Okay, and if it is incoherent, it is going to bowing around of dislocations around dispersoids. Okay, so they are not able to cut. Dislocations are going to bypass the dispersoids and thereby increasing the strength of that particular dispersion strengthening alloy. Okay, so we have completed precipitation strengthening mechanism. We have also completed dispersion strengthening mechanism. See, the concept remains same, both dispersion strengthening mechanism and the precipitation strengthening mechanism. Only thing is there is a difference between dispersoids and precipitates, which we have already discussed. So let me quickly give you very two basic problems, okay, based on the distance between the precipitates and the size of the precipitates, and rest you will do in the assignment also. Okay, so suppose I have an alloy, okay, aluminum alloy, and we are aging it. Okay, so we aged it, and after aging we have two conditions. So in first condition, the precipitate size was, let's say, suppose 30 nanometer. Okay, and the strength, you measured strength, the tau value, and that you got, say, 100 MPa. Okay, now the question is, if you change the, say, aging condition, and the precipitate size is now, say, 60 nanometer, then what is the strength? Okay, so you're talking about same alloy system, so G remains same, B will remain same, means material properties are going to remain same. Okay, so you are changing the aging condition, and because of the changing aging condition, precipitate size is changing. So strength is going is 100 MPa when precipitate size is 30 nanometer, and if precipitate size is 60 nanometer, what is the strength? And you are assuming that you have cutting of precipitates. Okay, this means it is on the left side from the peak age condition. Okay, so it is very simple, right? We discussed before that tau is directly proportional to root r. So you know what is the size here, right? So say if we consider size to be d diameter, which is 30 nanometer, so you know d1, and remember r is the radius here, right? So d1 is known and d2 is known, and d1 corresponding strength, say tau1, that is known 100 MPa. So you have to figure out what is tau2. So if you have this particular equation, right, you can write it down as tau1 by tau2 equal to root over r1 by root over r2. Okay, so now you know diameter is known, d1 and d2, so you know what is r1 is 15 and R2 is 30 nanometer. Okay, so you can now use this particular equation. You can find out what is tau 2, that is given by tau 1 root over R2 divided by root over R1. Now you have all the values. You know what is tau 1, you know what is R2, you know what is R1, so you can calculate what is tau 2. Okay, so this is one simple problem. Another one is related to the distance between the precipitate. That means we're talking about now bowing around the precipitate, okay, or bowing around of dislocations. So say again aluminum alloy we are talking about, and you have age date, right? So size is now larger because we are talking about bypassing. Okay? So say the size is larger. So let's talk about distance. So previously, say you had distance of lambda 1 as 1 micron meter, and then the distance, average distance, has increased to say lambda 2 as 2.5 micron meter. Okay, so you have age date and the distance, average distance between the particles, precipitates. It has increased from 1 micron meter to 2.5 micron meter, and the strength corresponding to this was supposed tau 1 as again 100 MPa. So you have to figure out what is going to be tau 2. Okay, and here you are assuming that dislocations are going to bypass. The precipitates. Okay. The previous one was related to cutting. This problem is related to bypassing. Okay. So here also we have discussed the formula, right? So stress required to bow a dislocation, that is given by GB by lambda. You remember, right? So we can write it here again. Tau 1 is equal to GB by lambda 1. Now GB will remain same because the material is same. So tau 2 here is GB by lambda 2. Okay, so we can write tau 1 by tau 2 as lambda 2 by lambda 1. GB will cancel out. Okay, now you know all the values. You see here tau 1 is known. Tau 1 here. Tau 1 is known, lambda 1 is known, lambda 2 is known. So you have to calculate what is tau 2. So tau 2 from this equation is given as tau 1 lambda 1 by lambda 2. So you can calculate, you know all the values, isn't it? So these are the two simplest problems related to precipitation strengthening, and you will know more in the assignments. Okay. So next we are going to discuss about solid solution strengthening.